Hey, this is Mark Lickman. In this video, I'm going to provide an update to the open source DIFI software used for certification. This repo I'm showing here, which you can find in the DIFI Consortium GitHub organization, or just Google for the DIFI certification code. This repo contains a few different things. There's the Wireshark dissector, a DIFI 101 tutorial here. There's some example DIFI PCAPs, and then the rest of the repo is essentially the certification software. This software can read in a live or recorded DIFI packet, either a stream or a PCAP, and then validate each packet against the DIFI specifications. It can also generate DIFI packets for testing devices that are fed a DIFI stream. And recently, we added support for DIFI 1.2.1. Now, the core of this software consists of this packet definition code. And each file here represents one type of DIFI packet of a certain version. So let's look at the context packets of 1.2.1 to see how this code works. So there's really two parts of each of these files. The first one is the packet definition, the structure here. And this uses a Python package called construct. And construct lets you define all of the fields in the packet, and then you can use it to actually parse packets. This includes enumerations, like the TSI value, and then there's some weird fields as well that I'll talk about. But this is a very convenient way to define the packet structure in a way that's pretty readable, I think, once you get used to it. And then it also acts as a way to encapsulate all the details that are needed to parse the packet. So very convenient. The second part of each of these files is a long list of validations that are run on each packet if desired. So each one of these represents a certain piece of the DIFI specification, like that the class ID has to be 1 for a context packet. And if any of these fail, there's a string that goes along with it. So when we're actually running the certification script, it'll log all of these strings, and then you can use that for debugging. It also uses, if any one of these fails, it considers it a non-compliant packet. And the script at the end will tell you the count of compliant packets and non-compliant packets for each type of packet. So let's look at one more example. Let's do the version packets for 1.1. These packets are a lot simpler. There are less validations. Look at this field right here, the year. So the construct library doesn't come with this data type here. This was created custom for DIFI, so we can look at the definition of it. And you can see that it's essentially a way to, with 7 bits, define the years since 2000. And that's a DIFI specific thing. I assume it came from Vita 49. But by adding this custom construct data type, which was only 1 line of Python, we were able to support that kind of unique data type, which was really nice. So you can make use of these construct definition files outside of the actual DIFI certification code that we'll get into in a second. Now, if you have any ideas for how you might use this, for different kind of DIFI tooling, definitely let me know. You can post an issue on the GitHub here. It doesn't have to be an actual issue. It can be like a suggestion or an idea. But yeah. So now let's dive into the actual certification code itself. There are 2 scripts in the root of the repo. One is called certify source, and the other is certify sync. Now, the certify source is meant to certify a DIFI source, which is something that produces DIFI, which means this code here is essentially just parsing packets and checking them to make sure they're all valid. It can read in a PCAP or process live UDP, either one. Now there's also the inverse, the certify sync, which is meant to certify something that consumes DIFI. So the certify sync script essentially just creates a stream of DIFI, like an example stream, and then it's sort of up to the vendor to certify that their software or device is doing what they think it should be doing. So there's less code, less logic. It's really just like a SIGGEN almost. The certify source is really the meat of the certification code. Now, because certify sync generates DIFI and certify source consumes it, we can run them together as sort of like an end-to-end test. And then there's also an option that's been added in to generate a PN11 BPSK signal as the actual data, like the samples in the data payload part of it. That way you can do sort of like a bit error rate test. The certify source, which parses the DIFI, after it does all the metadata and such, if you want it to, it will attempt to synchronize to the BPSK signal, demodulate, and then calculate bit error rate. All right, so now if you want to install any of this software in the root README, there are instructions for Ubuntu specifically, but it's a pretty straightforward Python package, and you can look at our requirements file. So if you're on Windows, it shouldn't be difficult. You'll have to either pip or conda install these requirements here. Now, it also contains an example of how to run the two scripts, so certify source and certify sync. So we're going to run these examples here and sort of show it working and show how to look at the results. So over in VS Code, I've got the repo cloned. Here's the root README. You can look at it nicely here. But we're going to, in one tab, we're going to run the certify sync script. So in this case, certify sync, we're going to run it for 10 seconds on port 50,003. The sample rate's pretty arbitrary. It's not actually going to change like how long it runs or how many packets. I guess it does change how many packets per second are created. Yeah. Bit depth of 8. It supports 8, 12, 16, I believe. All right, so if we'll get that ready to run. And then on the source side, we will run the source script. We have to tell it what port to look at. And then if we enable PN11, it's going to try to sync and demod the signal. The certify sync always includes PN11 as the data. But the certify source is not going to go through the effort of trying to receive it unless you specify it with this flag here. So if we run the source, which is looking for DIFI, it's going to start looking, and then once we start the generator here, which will run for 10 seconds, you'll see that this starts finding packets. And we can control C this one at any time, and it'll stop and start parsing the packets it found. That way it can run at really high sample rates. It doesn't have to run in real time. It's essentially, it'll run as fast as it can. And by using this record and then process paradigm, we're not limited by the processing speed. We're really only limited by the speed at which it can record raw packets, which is pretty high. It's similar to TCP dump. But as you can see, it then it recorded 1,000 packets. It's processing them, printing out bit error rate. And you don't really see anything else till the end. And then it tells you the compliance count. So in this case, they were all compliant, which makes sense because we were using like the sync without modifying it. So of course it was going to be valid. But if there was any error, in any of these packets, you would see that here. But there's a lot of other outputs that are generated. So all of the gray files here represent like new temporary files. So the first one is the summary of the certify source code. This one here we can look at. And this is YAML, pretty easy to read. The company name you can provide as like a command line argument. Same with product name. So that'll be used as part of the certification process. But it shows you how many, let's see, the sample rate, some high level metadata, the packet size, the code, the code version that was used to run it. Next we have the error log, which is empty essentially. We have a power spectral density, so this gets automatically generated. I think it uses the final packet of data to create it, or maybe it averages it, I don't remember. But it has like an automatic bandwidth measurement. I think it's a 3 dB bandwidth measurement here, which can be nice. And then we have the log of the sync, which is less critical here because this information was more on the input side of things. And the temporary PCAP that was created while we recorded the signal here, because it was recording and then processing. So that's pretty much it.